the equation of motion or maybe the Lagrangian, so on and so forth. Okay. So, we already know, if you give me some equations, you can work out what the symmetries are, and very early on we saw that they I mean this was the motivation for defining a group. So, they have to form a group. So, that is what you are guaranteed, but now we can ask a different question. Given a classical solution, to the equations of motion, how does G act on it? Okay. There are exactly two possibilities. Again, something which we saw explicitly. The first one is so let us pick let us just choose, let G be some element of the group. So, you can ask, so when we say that G is a symmetry of the equation of motion, in other words we know how G acts on the fields. Okay. So, by the way, here even though I am using a scalar field, if there are many fields, single scalar field, you can see that what I mean by that is a full set of fields in the theory. So, we know how this group acts on this on an arbitrary configuration. Obviously, you can work out what it acts on a classical configuration. So, the question is, so we take phi classical and act on it with G. So, the question is what happens. So, the one possibility is that it maps, it is invariant. So, it goes to so this arrow indicates the action of this element G. Okay. So, it goes to phi classical. So, we say that it is invariant. So, implies that the solution, the classical solution is invariant under G. So, possibility 2 is when it is not. Okay. Now, the key point here is that since it is the symmetry of the equations of motion, if it is not invariant, it has to go to another solution. It whatever is the G action, it will map solutions to solutions. Okay. So, then it goes to phi prime of classical. Again, by classical I indicate that it is a solution to the classical equations of motion or the Euler Lagrange equations of motion. Okay. And implies that the solution is not G invariant. Okay. So, there is a name which goes with this sort of thing. We say that so the symmetry, but G is indeed a symmetry of the theory. I mean, it is just that the solution is not. It is very much similar to the fact that we live in a world where there is no translation invariance. Okay. Does not mean that the fundamental interactions etc. I mean we expect them to be invariant under those things, and we put that as one of the axioms or whatever as input, but we live in a world which is where everything is hidden. Okay. So, the terminology for this is it should be correctly called hidden symmetry. This is what Coleman argued for, that it should be called hidden symmetry because the symmetry is there. It is not like there is anything just because the solution is not invariant does not mean anything about the symmetry of the theory. Okay. So, he wanted to call it hidden symmetry, but sadly he lost out to the rest of the world. He argued, and so out of respect to him we should actually remember that it is actually a hidden symmetry, because physically that is what is happening, but the rest of the world calls it, it says that the symmetry is broken, or to be more precise, symmetry is spontaneously broken. Okay. This is very different from you can always write as a, so when we are looking at systems, we look for systems which have certain symmetries, but you can, once you say that you do not want a certain symmetry, you can explicitly break the symmetry. Okay, but this is not quite in that category. This is the symmetry, the theory has the symmetry, but it is just that you are in a configuration or in a this thing where the symmetry is not an invariance. Okay, so this is called spontaneous symmetry breaking. Okay, so this looks very abstract, but we can start with examples, and I am going to for a change start with a StatMech example. Okay, so we will look at examples, and there is a reason for this. Is that there is a, it turns out there is a very nice connection between statistical mechanics and quantum mechanics, and it is roughly that you think of time, you replace it, go to imaginary time, you take t to become I beta, beta is inverse temperature, and there seems to be some correct connection between these things, and so that is one connection. The other connection is that if you look at many body theory in condensed matter physics, those are non-relativistic systems, but just for a moment, suppose we assume that we are going to look at time independent solutions just for simplicity, then there is not much of a difference between relativistic and non-relativistic systems, at least within that subclass. Okay, so you will find that what we might call Hamiltonian in our field theory could be mapped to some free energy in some StatMech system. Okay, it is a one-to-one map beautifully, it works. Okay, so and there you try to minimize or extremize the free energy. Here we can extremize the Hamiltonian or the energy, which as I explained to you is the same as extremizing the Lagrangian, because it is related to via a Legendre transformation. Okay, so the example is going to be deliberately from statistical mechanics to just to show you that whatever I am saying has a much larger regime of validity, but just to have a framework I always discuss relativistic field theories. Also it is my expertise. Okay, so the example is is the Ising model. So in the Ising model, at every lattice site there is a spin which can take up or down values. So sigma takes values in plus or minus 1, or more pictorially it can take two values which we sort of indicate by up or down. And so if in a continuum description at every, if you are at every lattice site, if you have a spin field, then you just sort of replace it by saying that there is a field which takes, which is Z2 valued and has some value at every point. Okay, so this theory has a symmetry which is sigma goes to minus sigma. We know that all this up spins you can call them down, you can call down up. Okay, so there is a symmetry. Of course you can break this symmetry by coupling it to a magnetic field or something, but we are not talking about that. We are assuming that it's just a simple nearest neighbor interaction. So this is a symmetry. So now you can ask what are the so let us look at the vacuum or the ground state lowest energy configuration. Okay, what would that be? So lowest energy configuration. So energy is in lattice nearest neighbor, some j sigma I sigma j. I should put a minus sign so that it lets parallel guys become lowest energies configurations is to have all of them lined up in some domain. Okay, but this is not unique, that exists for exactly the same energy. You can always flip all the signs and you can get something similar to this. Okay, so that is a degeneracy, and now you can see, so let us call this G. You can see that the action of G takes you from one ground state to another ground state. Okay, so suppose you are in this particular ground state, you can see that this I mean this other ground state is related to it by the Z2, but you would say that the Z2 is spontaneously broken. Okay. And so this is one example, and this is where the symmetry is a discrete symmetry. But coming back to this, here nowhere did I have to actually say that look, there is a discrete, the symmetry is discrete or continuous, it does not matter. Okay. So, so what we will do now is to look at an example in field theory. Now here I could, even here I could get a continuous symmetry by replacing these things by Heisenberg spins. Okay. So then these things can take there is a rotation worth of those things. Okay. So that is just a generalization of that, but I do not want to get on to that. So Heisenberg ferromagnet would be a natural generalization which will have a rotation symmetry. Okay. So let us look at field theory. So now example 1 is this one. Is the following. We just take, let us take n scalar fields. Okay. One thing is I just defined G here to be the full group of symmetries, but whenever I mean I will write out possibly some subgroup of it because I am going to focus on those guys, but the theory can have a lot more symmetries. Okay. So let us take G to be SON. You will see that in our example it will be an ON, but does not matter. So let us just take n scalar fields and I write them as a n tuple, and then choose a Lagrangian which is SON invariant. So, it is just so what is phi transpose phi? It is just okay. SON is a set of transformations which keeps this sort of combination invariant. Even this is invariant because it is actually d mu of phi 1 whole square plus d mu of phi 2 whole square plus so on and so forth. And this symmetry, since it is just a global symmetry, in sense it does not depend on coordinates, does not matter the derivative being there. Okay. Huh? Oh yes, this I am not allowed to do this. Thank you. Okay. So what we will do now is to consider two different examples of potential, and there is one potential which we will be coming back again and again. And do not for a moment think that I do not know other potentials, but in some sense you will see that that particular potential capture is the simplest one which will capture all the ideas that I need. Okay. So, we will, so first example is the following. So, let us just call it U1, I just choose it to be okay, and case 2 okay. So, this is the one which we already have seen in the earlier example where it was only one scalar field, but now I have n scalar fields. Okay. And how does the SON act? SON acts okay, let me pedantic get right up this way phi j, and it does not act on okay. So, implies it is a internal symmetry. That is one which does not act on the space time coordinates. So, it only acts in field space. This I index here is an index for the n scalar fields. Okay. And of course, R is an n by n matrix satisfying R transpose equal to 1, In fact, I do not need to put in the determinant condition, but because that is the continuous part of the group, I want to. So, I can break it up into a discrete Z2 and this thing which we know, and determinant R equal to plus 1. So, these are the two conditions I impose on this. Of course, we also know that R, once I do this, can be written as e power a, where a is any antisymmetric matrix, n by n matrix. Okay. So, we know all these things, and so now the question is, let us look at what is the classical vacuum. So, in most situations where you study when you talk of symmetry spontaneously broken, typically it is with respect to the ground state or the lowest energy configuration rather than an arbitrary configuration. You can, whatever I said can be done. I mean, here I did not make the assumption that this is the classical vacuum, but we will see for many physical things we would the first non-trivial solution you look at is the classical solution. Okay. So, the classical vacuum, so that would be the lowest energy state. So, obviously that is the one which is where phi is a constant. So, this term, when you go to the Hamiltonian thing, you just get a flip of signs and you get a sum of squares. We have done all that. So, all we need to do is to forget about this and think of phi as just a number, a constant, and minimize your action. Okay. So, but you look here, this has a minimum when it is just a quadratic this thing. So, it has a minimum at 0. So, case 1, it is just okay. Now, the question to you is what can we say about the symmetry of the solution? Anybody on this side? It's it's invariant under the full action of G, because if I start out this is equivalent to saying that this phi equal to all zeros, and any rotation of all zeros, the 0 vector is the vector which will remain a 0 vector in this n dimensional fictitious space. Okay. So, let us let me just define. So, let H be the group of symmetries of the classical. Okay, this will also form a group, obviously, again the same argument, but in this case here H is also equal to SON. Okay. So, the idea of spontaneous symmetry breaking is to say that H is a subgroup of G, strict subgroup. Okay. So, this is case 1. What about case 2? Now, again this is bounded from below. I have adjusted the constants obviously to make this have a 0. So, where is the 0? This is at phi dagger phi transpose phi equal to a square. Okay. Classical vacuum. Okay. So, now you can see that this is a set of points on a n minus 1 dimensional sphere. So, this the set of vacua. So, there are many vacua now, many solutions. Here it was the solution was unique, okay, but here solution is not unique. Rather the set of vacua are points on a n minus 1 dimensional sphere. Okay. Some of you may not know what this is, but if I put n equal to 3, you will see a normal 2 dimensional sphere, and if you take n equal to 2, you get a circle, and higher dimensions, these are just natural generalizations of that. Okay. So, if you have trouble picturing this, there are two ways out, do not picture it, okay, or put n equal to 3 if you then you want to have this vivid picture in your mind. Okay. So, both ways are fine. So, let us look at this. So, now the question is, let us pick a vacuum. Okay. For instance, a vacuum solution is of this n minus 1 times and put an a here. I am just solving that. I am putting phi 1 to phi 1 phi n minus 1 equal to 0, and phi n I am choosing it to be plus a. I could have chosen it to be minus a, but I do not care. I just choose one of them. Okay. So, now the question is, what is H? So, we know that if you take SON and act on these things, if I take an arbitrary SON, it will mix it, and in general it is like saying so let us put n equal to 3 because we want to picture things. So, if I choose a vector this way, if I do a rotation, arbitrary rotation, then I will go to some other thing. So, in general I will generate all the components back. So, it will be moving some motion on the 2 dimensional sphere when n equal to 3. Now, the question is, what is the subgroup which preserves this? It is SON minus 1. It is the set. So, let us take in 3 dimensions. If you pick a direction, the subgroup of rotations which preserves it is rotations which about that axis, but that is in 3 dimensions. So, and that picture is actually lousy in general. What you want to do is you want to look at rotations which mix all the 0 components and do not leave, which leave this untouched. Okay. That is SON minus 1, which will agree with the other case. If in 3 dimensions it becomes SO2. SO2 is the one which mixes x and y, leaves z untouched, for instance. Okay. So, in general you have to think of it in that fashion. So, H is very simple, it is SON minus 1, and clearly strictly a subgroup of SON. Of course, you could do this if you think of A as a free parameter. If you take A to 0, suddenly you find an enlargement of the symmetry, and then H becomes everything becomes 0, then it goes back to this case, even though it is not m square power 4, but it does not matter, it is some 4th power, but nevertheless it still has the same property that the ground state lowest configuration is same as out here. Okay. So, now we have something very nice, where H is a strict subgroup, and so this is a case where you have spontaneous symmetry breaking. Okay. So, you can see that there is a non-trivial set of vacua which are, so all of them have to have the same energy, all of them have same energy 0, that is why they are degenerate. Okay. Now, there is something very interesting which comes out of situations like this, where you have a continuous. So, this is not like you have a situation. So, yeah. So, so this is unlike the example of the Ising model, where it is a discrete group, this is a continuous group. Okay. So, there is a very nice result which is due to Goldstone, it is called Goldstone's theorem, which says the following. Okay. No, before that let us just discuss, before we discuss Goldstone's theorem, just I need one more bit of this thing. So, you can ask what are the set of transformations now. So, the in G which are not in H, okay, what would they be parameterized by? Do we know any set which parameterizes that? Exactly. So, it is the coset. So, it is a set of elements in G which is not in H. Okay. So, just a remark. coset G mod H parameterizes the broken okay. So now I am sort of yeah, and this is by the way true for whether G is continuous or not, but just I need one more small remark, which is if let us assume that G remark 1 or remark 2 is when G is continuous, G is continuous, then I will define something called dimension of the coset I need to explain some things out here. By when you have a continuous group, dimension cannot be the number of elements in that set because it is infinite. So, this is just the number of parameters. So, coming back to our example here, a dimension of SON will be equal to as many the number of parameters, that is the number of independent antisymmetric n by n matrices. So, that is n into n minus 1 by 2. Okay. So, in particular dimension of should be equal to dimension of SON, which is n into n minus 1 by 2 minus dimension of SON minus 1. So, I should just subtract by this, that will become n minus 1 into n minus 2 divided by 2. I can pull out the common factor, it is n minus 1, okay. And it is not unrelated to the fact that there are n minus 1 zeros out here, okay. Roughly it is the set of directions in which you could independent directions in which you could go, okay. So, now I am ready to state Goldstone's theorem. Let me write it again. Okay. So, let G be a continuous symmetry of a theory and H less than or equal to G. Just one comment, if suppose sometimes it can happen that H is some discrete group, in sense of counting dimension of a discrete group, what would it be? 0, okay. Just remember that, okay. If the group is broken down, okay. So, we will see one situation I can show you where you start out with SO2, okay, SO2 broken to SO1. What is SO1? Nothing, right, but actually you can break it down to some ZQ, which is a discrete group. In this kind of continuous counting it is 0, okay. So, this formula still holds if H is a discrete group, even though G can be continuous, it can be broken down to some discrete groups, but those do not count. So, it is only the continuous parts of H that matter, okay. And H is this thing is the symmetry of the vacua then there exists dim G mod H massless okay. By massless it means excitations which do not cost you energy, but that makes sense, right. If I am going to go from here to something where I do a slight rotation where it turns on something else, I can always do that infinitesimally, energy does not change. Okay. So, that is what one means by this. Okay. But in field theory we mean something slightly more, and that is what I want to show you. So, now I will be more since I want to be explicit, should I choose I will choose n equal to 2 okay, for starters. You can, whatever I say goes through for any higher these things, but let us choose. So, let us to illustrate this, let so according to, so application of this, it tells you in this example that implies that the when, so you can see that when G equal to H, then your dimension is 0, which is the first case. In this case there are no massless excitations. In fact, the only excitations have a mass given by the parameter, that m which we had written would be the mass of this thing. Okay, I will explain that a little bit more later. So, when G equal to SON and H equal to SON minus 1, then we expect n minus 1 massless excitations. What we mean by that is that there is no potential for that there are excitations which have no potential, not just quadratic, it is just that it does not matter what translations in that thing is completely invariant. That is what one means. Okay. And so, let us now choose an example of n equal to 2, so that I can be, let us choose n equal to 2, and so then G would be with of case 2, of course, G is now SO2 and H is actually okay, let us just for simplicity just say it is null. Okay. I will discuss again, we will come back to this example, there is a possibility of it not being some discrete subgroup, but for now I just sort of leave that, I think of it as 0. So, we repeat whatever we did here. So, phi vacuum is something like this. Okay. So, what we will do now is to expand, look for a solution. So, what we mean by excitations is to ask, it is with respect to this thing. So, what you do is you take your field and you write it as follows, you write it as phi vacuum, okay, plus say some chi, and so we look at chi and we expand about these things, but I will be more clever, I will choose chi in a slightly different manner. I will choose it as follows, I will choose phi not like this. Quite often in this course we would do something like this and expand things to all orders in this thing in phi, and you get an effective action. So, it is like you trade your field phi, I mean for this field chi. Okay. So, that is what you are doing. So, I want to write it in a slightly different manner. So, I will write this as phi for our example. So, this is the SO2 transformation which is broken, which acts on A. So, plus I will write an eta. So, my what I have done is I trade the field phi for two fields, one is an angle field theta and the other is this eta. Okay. So, we trade, so this is chi, the analog of chi here, we trade phi for two fields eta and chi and theta. Okay. And their excitations about the vacuum, if I switch off eta and theta both of them, I go back to the classical solution. So, I can think of asking taking them to be small, take eta and theta to be small, but what I will say does not actually require that. Okay. So, what we will do now is to plug this into the action and ask what happens. So, we have L which is a function of phi 1 and phi 2 now, which you rewrite as L of L tilde of eta and theta. Okay. So, first step is to work out what d mu of phi would look like. D mu can act on these guys. So, I get, I will do it a little fast, hopefully you won't mind. Okay. So, both I am not saying eta and theta are constants, they are fields. Okay. So, now you just got to go ahead and put this into the we need to put it into the so we need to compute d mu phi transpose, of course. I will let you work this out, and for and I will tell me what you get. Okay. So, one thing you can, so this will look, okay, here I will, by this I mean d mu theta plus, you will see something like this. Okay. And you may think there are cross terms, there are not, and dimensionally speaking, if you think of this as some kind of a length, you would see that this would come with some. Okay. There might be cross terms, you check those things. Okay. I won't write those things. Okay. What about the potential? Potential was but by definition it is independent. What is it, phi 1 square plus phi 2 square? You can see that the angle will completely disappear, it depends only on a plus eta whole square. Okay. So, now let us look at this thing. This may have a, I mean this looks like I mean, yeah, what am I trying to say? This thing is has a kinetic energy term for theta, but there is no potential energy for theta, it is completely flat. Okay. So, there is so this is your massless excitation. So, you can see that theta has no potential, and it costs no energy obviously to change its value. Okay. So, what about eta? Eta of course sees this full potential. Okay, you can expand it, and if you look at so this will have a term which will look like lambda by 2 eta no, the leading term, yeah, eta lambda, wait, let me just do this into 2 a eta whole square eta power 4 or higher powers plus eta cubed. Let me leave it at this. This is what you get. The a square cancels. So, the leading term is this sort of a thing, and so you get something which looks like, so this term is equal to lambda. So, you get 2 lambda a square eta square, which I will write as 4 lambda a square upon 2. Okay. And eta has mass square equal to 4 lambda a square. Okay. So, this object is precisely the what we will call the massless excitation. So, now I need to make a remark from quantum field theory. Suppose you have in quantum field theory you have the analog of a Klein-Gordon field, okay, which is just u of I being m square upon 2 phi square for a scalar field. When you quantize the theory, you find that the quanta of the theory are have mass m. Okay. So, the excitations in the quantum field theory of this classical field theory which we look at. Okay. So, that would correspond to the mass. So, in that sense the coefficient of the eta square piece, if you have higher order things, what you usually do is to call them interactions and you treat them separately. But what this will tell you is that this eta field has excitation which is with some mass square. So, this mass will be square root of this object, okay. But this theta has no this thing. So, it is a massless excitation or massless particle. So, in quantum field theory this field theta field becomes, okay, and since it is a scalar field, so this is called a Goldstone boson. So, theta is called a Goldstone okay. So, the content of Goldstone's theorem is to say that there is dim G minus dim H Goldstone bosons. Okay. There are certain funny symmetries called fermionic symmetries, for which you will find that this kind of the analogous excitations are fermionic. So, you can get Goldstone fermions, but so in theories with supersymmetry for instance that happens, but we will not be discussing that in this elementary course. So, this is the very important, I mean we have done it for this simple case, but what you will see is it is exactly similar to whatever happens here happens in the more general case which I looked at and even more general examples. Okay. So, for instance if you take spin systems like the Heisenberg antiferromagnets, so there again if you pick a ground state configuration where all the spins are lined up, obviously there exists the symmetry is broken, the rotation symmetry, and then you will expect Goldstone bosons. Those have a name, they are called magnons. Okay. So, various I mean there is a sense in which even phonons. So, what is happening is that if you are in a lattice, translation symmetry is broken, but there is subtlety because when I mean in understanding in these systems where the G acts on space time, when it is not an internal symmetry, things are when it is an internal symmetry, things are very clean. There are subtleties in this statement, but nevertheless I think I will make a sort of a quasi wrong statement to give you a feel for things, is that you break translation invariance in a crystal. So, what that implies is that you expect massless excitations, and so one for each direction, and so if you are in a 3-dimensional crystal, so you expect 3 massless excitations. What would you call them? They are called phonons. Similarly, if you have some so the vibrational modes or the phonons, when you quantize second quantize the many body theory, there again it is the same thing. Okay. So, this is a very very powerful theorem, it just tells you how many massless excitations that you have in the theory. Okay. And another point is that this symmetry as I have discussed is a global symmetry, it is constant in all the parameters were constant in space and time.
Is this, I mean, basically you parameterize in a very neat way as well, like
yes, yes, yeah.
So, is that sort of parameterization always there?
Yes, so that actually yes, there is. So, here I was very clever in parameterizing. If I had done it in this, I could do it in this fashion. So, let us for a moment do it, okay, and then let us write that phi would be let us call the doublet as chi 1 and chi 2. So, then I would write chi 1 and then I would write A plus chi 2. Okay. Then in all these cases you would not what would not be obvious is the following: you can expand it to second order and you will indeed see that there is a massless guy, but you would not be sure, you know, is it true to all orders or whatever, which is, but actually if you go back and think about its origin, it has to be true to all orders. Okay. But for that you have to have this clever parameterization. I am not saying you cannot see it in this. Yeah, the reason I chose, for instance, I chose n equal to 2 is because I can quickly write the explicit matrix for that. Okay. But in fact, let me show you the parameterization for SON in general, how we would do that. It is exactly like this, except here we wrote the rotation matrix which corresponds to the part which is not invariant. Okay. So, there I have to just write out elements of the coset, and that is not very hard. It will not be unique, but I can still write. So, let me just show you that for n greater than 2. Okay. Yeah.
Because there is two internal
yes.
two fields, doublet of fields. We can write down the potential. We can draw the potential.
Yes, yes. Yeah, actually, let me, maybe I should, instead of writing something more general, let me draw this picture for you. It is called the Mexican hat. It is called the Mexican hat potential. So, what we have is, yeah. So, this is a good idea, and so what we want to plot is u1, u2, u, which is a function of phi 1 and phi 2 in this space. Okay. So, let me first draw a circle of radius a. Oh, maybe I should draw the, what I will do is I will first draw the hat and then I will draw the coordinates or whatever, because I am not so good at drawing. Okay. So, how does it go? So, the Mexican hat looks like this. So, yeah, actually I will do it in this fashion. Yeah, I should have thought of this. Okay, I first plot it in the phi 1 phi 2 space. It is a double well potential. At 0 it is this thing, and to get the phi 2 thing I just think I just take about this and revolve it. So, you can see that, have you ever seen the Mexican sombrero or whatever? This is exactly, I mean, it looks exactly like that. So, a choice of vacuum, for instance, would be to choose, say, this one. Okay. So, now I can draw this surface of revolution like this. Okay. So, so what you can see here is that if you pick this particular point, the eta excitation is going up here, it sees this. So, this is the direction of the eta excitation, while this direction is the theta excitation. So, it is going along the flat potential. Okay. So, this is exactly the picture which you should remember, that there is, so this is the flat direction in which there is no. So, think of a marble rolling in this thing, and the marble chooses your vacuum. You can, if you just tap it a bit, it can go to the next point. There is no this thing, but if you try to, you need to give a much harder kick to make it go up the hill. Okay. And that harder kick is measured, if you wish, is the second derivative about this point, which is exactly this. Okay. So, the mass square can be written, if you wish, can be written as d square u by d eta square at or rather, okay, let us call it at eta square, d square u by d eta square at eta equal to 0, or I can rewrite in terms of the original radial variable, call phi 1 square plus phi 2 square as r square or something, d square u by d r square at r equal to a square. Okay. So, this is so what you can see here is that this is basically, that is all that is going on out here, but I mean the power of this statement here is that once you have a group structure in this thing, it is a continuous group. If it is a Lie group, then you can actually write out explicitly what it is. Okay. So, I think I'll stop here.